We are going to do a thing called triple integrals. So it's just like a grown-up version of double integrals. And a lot of the things you did in double, you will do in triple integrals. Now, triple integrals are a little bit harder to deal with. Obviously, there are going to be 3 of them. So a general triple integral will look like that. 3 integrals. There'll be some region R. Then there will be a function x, y, z. And the general way they describe it is dv. dv is typically going to be some permutation of dx, dy, dz. So that is in itself not that surprising. Would you agree? If you were thinking of what does a triple integral look like, it would probably, that's the kind of thing you'd guess it would be. The tricky part is that you can't really visualize it anymore. I'm going to just mute some things here. As soon as I have to go out and into mute. There we go. That's it. So we don't need to watch this, whatever this was. Here we go. You can't really visualize them anymore. Do you know how double integrals are a surface and it's the volume underneath the surface? You can still about visualize it. But when you do triple integrals, it pretty much becomes a 4th dimensional world. And the reason it's a 4th dimensional world, that if you call f of x, y, z, x squared plus y squared plus z squared, as an example, technically speaking, you could write it like this, which is a 4-dimensional world. 3 independent variables plus 1 dependent variable. Good luck sketching a 4th dimensional surface, right? I'm not even sure it's a 4th dimensional surface. It could be a 4th dimensional volume. It's a 4th dimensional something. So all bets are off. You can only really process it through the algebra. Now you might say, well, what on earth am I calculating then when I get a triple integral? Well, give you an example. Can you imagine in 3D space, you have a big sphere, right? And that big sphere is region R, right? The whole surface, right? Not just the surface, but the inside, right? The whole sphere, right? The whole kit and caboodle. Can you imagine that every single point of that sphere has a temperature? And the temperature is given by, say, this formula here. So can you imagine at the center, it might be quite cool, but on the surface, because the X, Ys, and Zs are bigger, it's much hotter. Then when you do the triple integral, what you're essentially doing is adding up the temperatures in every single point inside that sphere. So the answer you get could be thought of as the total amount of heat energy contained inside that sphere. Does that kind of help you visualize what you might be getting, right? So people in the world of physics and so on, they like triple integrals for that reason. Now, there's a special case. Do you know if you do a triple integral over a 3D region called R of 1, right? So in other words, f of x, y, z is the constant 1. What do you think that would give you?
The volume of the region.
Yep. And here's another special one. Imagine over this 3-dimensional region R, you did this triple integral, and you used the density function as your f(x, y, z). What would that get you?
The mass.
Okay, so there are 2 very special applications of triple integrals, but in general, you're just doing algebra stuff. So you can't really visualize it as a three-dimensional shape. I don't think anybody in the human race can think four-dimensional space. If you have a brain that's capable of doing that, you'll be famous, if nothing else. Okay, so how do we do this? Well, let's start with the simplest case. That's going to be the function, right? The f of xy. And I'm going to do it from z equals 1 to z equals 2, y equals 0 to y equals 1, and x equals 0 to x equals 1. And what will be the order of the variables based on these limits of integration? So who goes first?
It'll be dz, dy, dx.
Now, you are allowed to permutate, different situations. Can you imagine that sometimes you might do the x, then the y, then the z? I guess you could even do y, zx, right? Anything is allowed, as long as you keep the limits of integration matched with this. So it's just pretty much going to be a big version of the 2D one. So you start off with that guy. So that's going to be the integral from x0 to x1, y0 to y1, and whatever that answer is, we'll do a dy dx on it. Okay, let's see. With respect to z, won't this guy become x squared z? With respect to z, this guy will become yz. And with respect to z, this guy becomes negative z squared. And won't we evaluate it from z equals 1 to z equals 2? Does that seem pretty straightforward? Any questions so far, or we keeping, looks good? Okay, so I'm just going to do let's see what you get. You plug in 2, you get 2x squared plus 2y take away 4. And then when you plug in 1, you get an x squared plus a y take away a 1. Okay, that take away that leaves me an x squared, that take away that gives me a y, that take away a negative gives me an add, so I have this guy. Essentially, don't we now have just a double integral? I'm going to take this one to the end, but a lot of the questions, when I get to a stage where both of these are numbers, I'm just going to do my ... thing, right? So we don't spend ages just watching something that you could do in your own time. Okay, so we're doing it with y's now. So let's see what that looks like. With respect to y, that gets you an x squared y. That gets you a 1/2 y squared, and that guy gets you 3y. And we're going to do it from y equals 0 to y equals 1. And that's 1's going to get me an x squared. That one there is going to get me a 1/2. That one there is going to get negative 3, take away nothing, so don't care about it. Get to there. We agree, plug in zeros, use a load of zeros. This is a Calc 2 question now. I'm going to combine them and do the antiderivative at the same time. So add 1 to power, divide by new power. This guy is actually negative 2.5, which is negative 5/2. So its antiderivative is this guy, evaluated at 0 and 1. That gets me 1/3 take away 5/2 minus nothing. And this guy here ends up being, well, if I turn them into 6, it looks like it's going to be negative 14. No, it's not. 2 of them, 15 of them, so negative 13.6. Are we cool with that? Now, what does the triple integral of this function represent? Who knows? But I can tell you its answer is a number. And negatives can happen, positives can happen, zeros can happen, right? All things are possible, except when it's the two special cases. If that's a 1, this better be a positive number. Agreed? And this is mass. This better be a positive number, right? But apart from those two special cases, Reese, you had a question. What is it?
I'm confused as to how you can find the volume by either doing double integrals or triple integrals. I mean, like, doesn't integrating add to the power? So like when you integrate with dz, you get power 1 d. Well, I'm just confused. So like double integral all of fxy with respect to dy and dx, and then triple integral with fxyz with respect to dz, dy, dx. Doesn't a triple integral like yield a fourth dimensional thing? I'm confused.
A triple integral generates a number, right? Whenever you do this, once you fill it in with numbers and expressions, the final answer will always be a number. Now that number can represent the volume of a shape, because what I'm basically doing is, for this three-dimensional region R, I'm associating the value of 1 for every point inside it. So 1 times its volume is its volume. In this situation, the mass one, for every single point inside that region, that 3D region, R is three-dimensional, and it's a whole solid region. For every single one of them, I'm associating what its mass is. So when I integrate over the triple integral, I'm basically finding the mass of the whole object. Now, you're saying you're confused that a second derivative or a third derivative can generate volume.
You mean integral?
A triple integral of 1 will generate a volume. A triple integral of just this generates a number that might mean something, but what it means is totally irrelevant to the process. I mean, I don't know what that negative 1316 is telling me about this, but I still know how to calculate it. Now, maybe somebody who's way into fourth dimensional math might say, that number tells me something. But conceptually, you're going to have a hard time if you try and visualize these. You will just give your brain a headache. You can't think in 4D. Don't even try. It's not a good process. You just have to trust the math and say, triple integrals get me this, and this is how I find them, and maybe just leave it at that, because anything else I don't think is constructive. I don't think I've answered your question about I'm confused. I guess what I'm saying is just don't be confused. Just trust the math. So let's up the ante to a more difficult version of this one. And I'm basically copying the way the book, the way the software has done this guy. This is basically question 1, or at least one like it. Now, do you know, in this particular question, can you see that the limits of integration, at least some of them, are not numbers anymore, but are functions in terms of the other guys, right? Now, when you see dz, dx, dy, does it not mean these are z's, these are x's, and these are y's? So here goes. I'll do this one first. So it's going to be y equals 0 to y equals 1. This represents x equals y to x equals 3y. And this fella here is going to get integrated in the usual way. Well, 12xy integrated with respect to y just gives you 12xyz, but then it's evaluated at z equals 0 to z equals x plus y. This is a good example of why I like to label the limits of integration. If you just put in the basic values, isn't it very easy to lose track of what something is representing? You know, is this representing x equals y, or is this z equals y, or what the heck is it? But now it's a little bit clearer. Well, let's see what we get. We get y equals 0 to y equals 1, x equals y to x equals 3y, and those two guys. Now, if you plug in x plus y for z, you get 12 lots of xy, x plus y, take away nothing. And distribute this, you get 12x squared y plus 12xy squared dx dy. Are you comfortable about the pass-through? The first integral is now complete. If you do this correctly, shouldn't this expression here only contain x's and y's? Agreed? If this expression here has a z left over, like a little orphan z cubed or something like that, stop, because you've screwed up, right? Now, I'm about to do a dx now, right? I'm about to integrate this with respect to x. So when I'm finished, shouldn't the thing that be left only have y's in it, no orphan x's, right? Every time you do an integration, doesn't one of the variables disappear in the integration process? And so you may start off with 3 variables, and then you get 2, and then finally you only have 1, and that'll be you finished. So we're now doing the next guy, which is him. Well, with respect to x, add 1 to the power, you get x cubed. Divide by that new power, you get 4. So that's going to be 4x cubed y. This fella, you add a power, you get x squared. Divide by that, you get 6x squared y squared. Then it's going to be evaluated at these two places. Continuing with this question. Plug in 3y. That's going to be 4 3y cubed y plus 6 3y squared y squared. Yeah. Take away, because it took up too much room, 4 y cubed y plus 6 y squared dy. This guy here gets you 3, 9, 27. 4 times 27 is 108. Y to the 4s. What's this? 3y squared is going to get 9y squared. 9 5s, 9 6s is 54. Y to the 4s. Take away 4y to the 4s plus 6y to the 4s. Good grief. Everything is a power of 4. That's unusual. So that guy and that guy gets me 162. Take away 10. I make that 152y to the 4. Right. Okay, at this point here, can I just say it's Calc 2 and you finish it the usual way? Reese, do you have a question?
Well, one final question. So, like, why does a double integral produce a three-dimensional result? But how come a three triple integral doesn't produce a fourth dimensional result? Like-
Okay, so your question is, when you do a double, right, let's wind back here.
When you do a double integral,
Right.
you get the volume, which is three.
Well, not always. What do you get if you do a double integral of 1?
You get the area, which is two.
Right.
dimensional.
So what do you get if you do a triple integral of 1?
You get three-dimensional, but
Right. So that's an area
but
of the region D.
oops, sorry.
Right? And this is going to be the volume of the region R. Now,
Well,
if you stick in, I'm getting to your point. If you stick in a certain function here and you do a dA, can't you create a volume of a shape that maybe a surface that looks something like this, right? It's got a
Yes.
curve, right? Now, if
yes.
you do a triple integral of a function dv, you will get, and you can't draw it anymore, you will get a 3D thing over a 3D thing, and you will be essentially finding the volume of a 4D thing.
That's what we're doing. So
Right.
why we get a three-dimensional result, the volume, rather than a four-dimensional result?
Well, if this is a function that represents the two different surfaces in 4D, in 3D space, which I can't imagine, so I'm not going to try. If you took two regions in 3D space and you put them together in some interdimensional way, this integral would find the volume of that 4D object. And you're just hurting my brain trying to think that through.
What about the volume of the 3D object?
Well, to get a volume of a 3D object, you use 1.
Okay, but though again, that's not what we're doing.
I think it is what we're doing.
No, we're taking the triple integral of a function, not one. So
Right, and if you do a triple integral of a function, you will be finding the volume of a fourth dimensional object.
okay, thank you for clarifying.
Right. Do not go down that rabbit hole of trying to figure out what the heck this is. Can you all see the problem? I'm sounding angry here. I'm not angry. I'm just, my brain is hurting because my brain is trying to process this now. Don't try and process this. It's not a good idea. My brain is just going to have a hard time trying to figure out what a 4D thing looks like. And I don't know what a 4D thing looks like because I'm not an alien that lives in 4D world. I'm a human that lives in 3D world. And that's kind of hard for me anyway, in the best of times. So are we getting cool that this is best thought of as an algebraic process and just go for it? And the answer will be a number. And that number will mean something in 4D or 3D or whatever D it happens to be, but it's still going to be correct. So we have to have that ability to kind of hold back. Right. These questions do take a long time, and I've forgotten how long they really do take. So I'm going to go in a little bit and maybe cut some corners here. Okay, there's my next guy. So here's our region in 3D space. This here represents the function that we're going to do the triple integral to. It only has x's and y's in it, but it could have x, y's, and z's. That wouldn't be a big issue. And I'm going to focus on this fella. So we're going to do from 2 to 3. It's okay. And we're going to do x equals 0 to x equals 2z. And this fella. Now, if you integrate x e to the negative y with respect to y, what is the antiderivative of this guy?
Negative xe to the negative y.
Thank goodness. It's so easy to get that and make it think it's harder. Isn't that x just like saying 5e to the negative y? I mean, that's really all it's saying. So we are going to be taking negative x, e to the negative y, and evaluating it at y equals 0 to y equals the natural log of x. And then we'll do a dx dy later. Well, let's focus on what that looks like. I'm kind of doing it over here because I think it means I don't have to keep writing this stuff. You go negative x, e to the negative log x, take away negative x, e to the 0. Okay, e to the 0 is 1. Agreed? Negative of negative x is plus x. So that's what you get out of that guy. So there's going to be a plus x here. Now, while I'm writing this down, think about what the other piece of this puzzle. This is horrible, but if you think about it, it actually does become something really nice. You just have to know how to deal with it. Okay. Can't that fella there, right, this guy here, be written as something else? So here's the algebra trick. What is that guy simplified down to?
1 over x.
Yes. Now, if some of you are puzzling where that comes from, here goes. Does it help to think of that as being this? Can you see it now?
Yes.
Now, you stick a negative x in front of that, don't you just negative x times that, and bingo, wow, negative 1. A lot nicer than if you left it alone. If you left this thing like that, can you imagine that your next step's going to be integrate this? And if you try and integrate this, you're not going to have a nice time of it. I'm not sure how I would do it. I'd probably do it as an integration by parts or something, but I certainly wouldn't want to choose to do it. Now this here, on the other hand, is so much easier. And I'm going to go a dot, dot, dot here. Would you agree that that is really not that hard to finish off? Isn't it just like a normal double integral with some replacements and then some numbers at the end? Are we good? Right, I want to do a side issue here before I do another one. Let's talk about what you can and can't do to make your life easier with triple integrals. So 1 to 2, 3 to 4, 5 to 6, some arbitrary function of x, y, z. Let's suppose it was dx, dy, dz. Okay. So that could be x cubed plus y squared plus z, right? Any combination. Am I allowed to switch the order of integration if everybody is numbers?
Yes.
Right. And if I chose to, and I'm just going to randomly pick one. If I chose to do this order, basically, won't I be doing the z's first, followed by the x and then the y? So provided all three integrals are numbers, right? They're all limits of integrations are numbers. Can't you choose the order in which you want to do them? Can you imagine a situation where it might be better to do the x's before you do the y's, before you do the z's? You know, just because you can see the math that they're going to become much easier to do, right? So if you do notice that that's going to happen, then maybe you should shuffle the cards a little bit. Different story. Still numbers. Yes, question?
Wouldn't the order be dy, dz, dx?
Let's see. The z's are 1, 2, so the z's go first.
I
The
see. Yeah.
x's are 5,
Never
6.
mind.
Yeah, we're good.
I get it.
Right. That's probably another reason why it's a really cool idea to stick. I know they never do it in the textbook, and I was being careless here, but isn't it helpful to stick z equals next to things and x equals? So when you start shuffling the cards, you keep track of which one belongs with which variable. Now, what about this one? Again, I'm being lazy about who goes where, so maybe I should put in some numbers and variables. You remember we looked at some situations where things were variable separable? You know, where the x's and y's could be separate. Do you know that that same process is allowed in this situation as well, isn't it? Would you agree that these can be separated out? In that case, wouldn't it be a good idea to do maybe the x's? And the y's, and finally, the z's. Could you imagine a situation where that might be less work?
100%.
Right. So you're always, what's the phrase I'm thinking for? It is a good idea to always look at a question and see if there's an efficient way of tackling it. Your job is not to blindly, follow a, you do this, you do this, you do this. If you can see a situation where maybe something can be done in a better order, a quicker order, or whatever way I want to phrase it, I can't think of other phrases, then you should always be on the lookout for that. Now, doesn't that work exactly the same thing? I'm about to blow everybody's brain. You ready for this? If we can do single integrals, which is Calc 2, and we know we can do double integrals, and we've done a lot with double integrals, we've started with triple integrals. Isn't it possible to do quadruple integrals? You'll be glad to know we don't in this course. But would you agree that quadruple integrals are just the same as triple integrals? You just do more work. And these are the nicest ones, right? But couldn't you do ones where this went from here to here and this went, you could introduce variables all the way. If you do that, isn't the only rule the last one has to be numbers? And as long as you have that, now what is a God in Himmel? If this is a fourth dimensional function, isn't it a fifth dimensional world? So now we're integrating fifth dimensional things. And if fourth dimensional things annoy my brain, I'd probably start swearing if I tried to figure out what fifth dimensional objects were doing. The cool thing about math is we could do 11 dimensional objects, couldn't we? I mean, I could do an 11 dimensional integral. I haven't a clue why I'd want to, but if you gave me it, I could do it. So we always should be on that kind of, yeah, okay, I can do that. Yeah, I'm not going to let it freak me out, you know. I can do the math. Right, this next one, I'm not sure why I'm picking it, but there's a reason I wouldn't have kind of had note to self. Okay, I'll write it down first and then I'll figure out why I chose this question. The integral is going to go 0 to pi, which is what x is equal to. Oh yeah, I remember why I wanted to do this now. Z is 0 to 2, and y is 0 to the square root of 4 take away z squared, and the function is z sine x dy dz dx. Now, if these were numbers, if this was y equals 0 to y equals 4, wouldn't this be a variable separable situation? I could just do 3 single integrals. Unfortunately, that guy there contains z's. Great. So that stops that shortcut from happening. On the other hand, do any of these involve x's?
Nope.
Do any of these limits of integration have x's in them? And the answer is no. So couldn't I at least do this? In other words, separate out the sine x and have the other two together. Now, when you look at this guy, is this guy a pretty standard run-of-the-mill double integral from last week? Right. So can't you just do it as a double integral, get whatever it is, and then get this? So that'll be a number when you're finished, right? And this will be a number, and then you multiply the two together, and you're over with. So I'm just saying, like, that would be a kind of slightly less work to do, right? And now,
Would that be Z dy dz?
thank you. Yeah. We cool about that? Right. So I'll leave that one as is. Let's see what we got time. We got enough time? Yeah, we can do this. Right, while I'm getting set up, why don't you lot say hi? Okay, hopefully everybody's had a chance to have attendance. Right, here's a double integral. The region is described in terms of relationships between the x, y, and z variables here. Now, I need to set this fella up. Now, dv is going to have an x, a y, and a z in it, and we know that we can switch them around any way you like. But some ways work and other ways, you know, order to do things. So, would you agree that those two guys are pretty much telling me the z values to use. In other words, I am going to do z from x squared take away 1 to z equals 1 minus x squared. And that means I'm going to do dz first. Would you agree that this is telling me who the y's are going to go for? So I'm going to go y equals 0 to y equals 4, and I'm going to do dy. But I still have the problem about who the x's are going to be.
Aren't the x's going to be negative 1 and 1?
Yes? Tell us why.
How I think about it, and I don't know if this is right, is you kind of want z to be 0. So you make it so that x will make z 0.
Ah, okay. So you got a negative 1 to 1. Is that your thought process? So if I draw the x-z axis, right? So I know it's the 3D space, but imagine that I just looked at the wall where x and z were, right? Now, x squared minus 1. X squared minus 1 looks something like, darn it, if I can draw x squared minus 1 easily. It goes like that, right? And doesn't z equals 1 minus x squared go like that? And is it the place where they intersect negative 1 to 1? So that's the reason why it's negative 1 to 1. It's not that these are equal to 0 at that place, which they truly are. But can you imagine that you might get a situation where it's 0 to 2? So it's the intersection of those. It's the places where they two things meet that generates my x, rather than it's 0. Right? But you were definitely got the right answer, which is good. But can you now see why it's the right answer? So if I change this guy to x squared minus 4 and 5 minus x squared, right? Then when you set them equal to each other, and I hope I've set this up right. Okay, I've kind of set it up badly, but at least it's doable. Can you see that your x is going to be plus or minus those two numbers? Right, now that I've set this guy up, are we comfortable about the process of, you know, do this fella with respect to z? Then once you get that answer, do it with respect to y. And then once you get that answer, do it with respect to x. Are we comfortable? The setting up was the hard part. The doing is kind of, hopefully, it's getting more like a process now. From what I can see, isn't it just going to be some ugly polynomial? Right. So nothing particularly to see here. Now, let's see if I can. We might have time. Let's go for it. We have a triple integral of e of this fella. E, D, R, any letter of the alphabet you like. E, I'd call them all R if it was me, but I don't have that power. We need to set up who to do first, who to do second, who to do third, right? X, Y, or Z. So looking at this, Do you see that that needs to be the first integral? Why? Because it contains x's and y's in it. So if you do z equals x take away y, and then z equals x add y, that'll get that guy. Done. Now, y or x is next. What goes here? The second integral, limit of integration, y or x's?
Why?
Why?
Correct. Now I get to say y, as in the question,
Because it has an X in it.
right? And this guy is 0 to 4. So if you imagine I mucked about with that even more, the variable that has the other two letters, right? That's always going to be your first. So, I mean, in the next story, it might be x is between y plus z squared and y minus z squared, right? It might say that kind of x in the middle with that on the outside. The guy that has two variables, always the first one, right? Once he's taken care of, if they're both numbers, it doesn't matter. Pick whatever order you feel like, right? X, Y, Y, X. If they're both limits of integration or numbers, you're fine. But if one of them has the other in its variable list, like here, he must go second. And then always finish with numbers. So that's how you tell the order of integration. So I'm going to go Z, then Y, then X. Does that order make sense? How you decide what the right order to do something in? If you screw up the order, if I shuffle these cards around, you will know that you've screwed up, because won't you have an X or a Y orphan left over someplace? And you know there shouldn't be any more X's left, but how come there's one here, right? Or you'll get to the end and the answer will not be a number, because these are always numbers when you're finished, right? The answer at the end has got a Y in it or something, and you know that's a wrong thing. So I think theoretically, isn't there 6 permutations? Yes.
If
Ben,
the
or Jason.
z bounds only had like a single variable, would they the y and the z be interchangeable?
Oh, let's pretend we got one. Suppose it was this guy. We'll keep the Y the same, and we'll give the Z just one of the variables, right? Let's give the Z a Y. Okay. Now we want to set up the order of integration to take this into account. I'm going to do the easy one first. Would you agree that x equals 1 to 4 would be the way to go, right? So that's that done. I've got 2 more guys to come up in a minute, right? So which one of these goes second? Because the question was, are they interchangeable? Well, let's find out if they are or not.
Okay.
Which
so
one do you
that
think?
one's definitely not, because you'd have to do the z first.
Correct. We want to explain to the people who are watching why that has to be done first.
Because if you did that one second, there'd be more y's.
Right,
then,
and
like,
there'd be a Y left over as an orphan, wouldn't there, later on?
yeah. But if they're both x's, would then
Right. If they were both X's, interchange them, won't have a problem. So you sometimes would have to think about it. If I put this one first and that one second, what would happen? Just think about the future. And if the future is, oh God, I'm going to have a Y left over and I've already used up the Y's, that's a bad sign, right? I call them orphans, right? If there's an orphan variable left over, you probably should change the order to take care of that. Ben, what are you asking?
So if you weren't trying to take the integral with respect to one variable and it was in your last integration, then you'd have a variable left over. But technically, since you never took the integration with respect to that variable, that wouldn't be a problem, right?
If you have a variable left over at the end, it is a problem. You must have numbers at the last step, if that's what you're asking.
Don't worry about it. Sorry.
You've thought it through? Okay. And that is perfect timing. So